Thank you for the invitation to give a talk in celebration of the Structural Geology and Tectonics Division's 40th anniversary. The title of my talk is Energy Budget of Orogenesis and the Implications of a Lazy Earth. And I need to thank my colleagues in the subduction zones and 4D landscapes and seascapes working group for helping develop the ideas in the talk. This is a bit of an idea talk, but these are not new ideas. Elliott analyzed the energy budget of Orogenesis over 40 years ago, a few years before the establishment of the SG&T division. In this talk, I'm going to revisit those old ideas, add a few of my own, and then highlight some examples. So we know that plate tectonics and orogenesis results from the Earth shedding its heat. Energy drives deformation, and this is why geodynamic models that simulate crustal deformation implement both mass conservation and energy balance as part of their governing physics. Deformational processes convert energy from one form to another. In one example, fault slip converts stored strain energy into frictional heat, seismic shaking, and breakdown energy, which is the energy required to advance slip along the fault and includes damage. Because these work terms are formulated as force times distance, the area under the stress strain versus slip distance curve captures these energy components. In this cartoon, I drew a hypothetical representation of how this stress might break down with increasing slip. On the right, Aubin's recent experiments have been able to carefully document this transition of shear stress with the growth of the fault. So we're seeing new data that constrain these energetic terms. The bottom example shows dislocations within a quartz crystal. The collide of dislocations out of the crystal reduces strain energy and results in distortion of this crystal. One of the most profound applications of the energy budget is that it allows us to directly relate deformation to hazards. We measure earthquake size in energy terms, and we measure eruption size in terms of mass moved and eruption column height, which are expressions of kinetic energy. So when the rate of energy input to a system exceeds the rate of energy output, then our system is accumulating energy that might be released in earthquakes, in eruptions, and also landslides. I'll be considering mass transport within the orogenic energy budget because surface processes play a role in modulating mountain building. So the size of the earthquake, eruption, or landslide depends on the energy that's available in the system at the time that the event is triggered. When it comes to crustal deformation, we have different forms of energy. One is work. I mentioned this before, and it's the energy it takes to move a mass through a certain distance and under a certain force. Another is heat. A third is chemical energy, which plays a large role in metamorphic reactions. In this talk, I'm going to focus on the role of heat and work within upper crustal deformation, but the budget here can be modified to include the role of chemical reaction, and probably should be. This finishes the introduction to the talk, and I'll now outline the first order energy budget before describing how energy inputs and outputs vary across earthquake and eruptive cycles, and then implications for a lazy Earth. We can divide the energy inputs into three broad components. First, tectonic work comes from the convergence across the margin. Then there's heat, both the radiogenic heat produced within the crust, HR, as well as heat flux from the lower crust and asthenosphere. The third energy input is gravitational potential energy. This term can change as mass is added either as precipitation from the atmosphere or upwelling from the lower crust. The energy that comes into the orogenic system can be consumed by deformation, uplift, and released within earthquake events, either along the megathrust or along these upper crustal faults. The earthquakes produce frictional heat as well as ground shaking as first order terms. As mentioned earlier, damage is also a product of earthquakes, but to make a more manageable budget for the whole system, I'm excluding that from this first order energy budget. Energy is stored as uplift against gravity, and and also with internal work of deformation. I'm not including here the equations for each of these terms, but you can find them in several papers. Energy within the orogenic system is also released by tsunamis, landslides, and the heat and kinetic energy of mass erupted from volcanoes. Many other terms can be added to this formulation. The important terms may depend on the question that you're investigating. I want to come back and revisit the gravitational potential energy and the internal work. Unlike the other terms on the right-hand side, like heat, that are lost to the system, the gravitational potential energy and internal work are conservative energy terms. This means that they can either store or release energy. For example, internal work can increase between earthquakes as strain builds in the inner seismic period, and then release that stored energy during earthquake events. I find this internal work really interesting. Up until now, I've described this using elasticity, but I don't need to tell this crowd that crustal rocks and mountain belts have a lot of fabric and permanent deformation. For example, the development of cleavage fabric, microfracturing, pressure solution folding, all of these mechanisms reduce internal work so that not all of the accumulated internal work gets released by hazards. So how much gets preserved in permanent deformation and how much is available for hazards? That's an outstanding question. All right, now we're going to look at the various inputs to the system over time. The first two, tectonic work and radiogenic heat, can be considered relatively constant during the period of orogenesis. We can add to this the upwelling of material from the lower crust, which provides buoyancy and heat that might, for the most part, be constant over time, but there may be some pulses of duration that have greater flux. And then we can add to the inputs the precipitation, which varies over much shorter time periods than the other inputs and includes large punctuated storms. I've added a lot of question marks here because there's much we don't know about these inputs and have yet to constrain. So now let's look at the energy outputs over time, which gives us a chance to explore the interactions among various processes. I'll start with the simplified elastic model of energy across earthquake cycles. Following the elastic rebound model, energy is stored as internal work and uplift against gravity, the conservative terms, and this internal work is released during earthquake events. This megathrust earthquake has complete stress drop and produces a tsunami in blue, along with frictional heat and seismic energy in pink. Over here is an example of an upper crust earthquake, which has lesser stress drop and smaller changes in gravitational potential, heat, and seismic energy. The purple line that I just added separates the conservative terms from the energy lost to the system. Everything below purple reflects energy within the system that's available to drive further deformation. We can see direct evidence of the changing energy available using scaled physical experiments that include a stress gauge. Each time that new faults grow within the accretionary sandpack, the force measured at the back wall drops. We see a similar drop in work with each episode of fault growth as with slip events on the conceptualization on the left. The strain movie that I'm showing at the bottom is one of my favorite animations. The strains are derived from digital image correlation from high-speed camera images looking at the interval just preceding new accretionary fault growth. Before that new forethrust develops, the shear bands migrate through the sandpack in response to accumulating internal work. The level of detail available in these analog experiments is rather impressive and inspires many questions about the energy budget within fault systems. Coming back to the energy outputs, so far we've only talked about earthquakes. Here I've added volcanic eruptions to the energy outputs in purple. The volcanic arc is always releasing some heat and volatiles through epithermal circulation, but then with the eruption, there's a great increase in heat and kinetic energy of erupted material. Also, the eruption decreases the gravitational potential energy as the magma system deflates. Now I've added mass transport energy in orange. Sediment flux can increase in response to precipitation fluctuations, including large storms, and also in response to earthquake shaking and volcanic eruptions. I've added here a lot of question marks on top of this to indicate once again that we don't really have good constraints on the relative contribution of these different elements to the energy budget. A variety of studies have tackled this problem, often looking at just components of the orogenic margin. I'll show you very briefly a couple studies that have looked at the accretionary wedge deformation. So up here on the top, we took information from sandbox experiments of accretion. Using digital image correlation, we can get the strain map. We've got a force gauge to get the stress. And so what Jess McBeck did was estimate from that and the rheology of the sandpack what the different components of work against gravity, frictional work, and internal work would be, and then was able to validate that with the force gauge for the external work. And so what we learned is that frictional work and internal work dominate the accretionary wedge work budget. Jeff then followed that up with another study looking at scaling. We can look at the scale of the physical experiment, but what happens when we scale that up to the crust? And so this plot here is showing the energy budget for that sort of laboratory scale accretion, and the one here in the middle is for the crustal scale accretion. And what we learned in that study is that the partitioning of work into these different terms is quite sensitive to the rheology. We were using elastic stiffness in these simple models. And it was also sensitive to the slip weakening distance, which impacts the frictional heat. We still saw the frictional heat and internal work dominated, but as I mentioned, we're using elastic rheology. So what happens when we consider the inelasticity that we know happens in the crust? We can consider that by acknowledging that not all of the internal work that's accumulated is going to be available for hazards, and some it's going to go into inelastic deformation. Estimates over 40 years ago by Elliott found that pressure solution in the upper crust might dominate the energy budget of bolt and thrust belts. And more recently, Mead did another analysis refining Elliott's approach and using data from Taiwan that also showed that this internal work can dominate the budget. But there's still a lot we don't know about the long-term inelastic deformation within orogenic belts, and these terms are not yet well constrained. Furthermore, the inelastic deformation that occurs in one part of the convergent margin may be very different than the inelastic deformation that occurs at other parts of the margin and different depths. Laboratory experiments have told us that the deformation mechanism that dominates any particular location in the crust depends on the pressure, temperature, and strain rate. This deformation mechanism map for calcite from over 40 years ago shows that while calcite prefers to deform by pressure solution at some pressures and temperatures, at other conditions that the calcite may more efficiently deform by dislocation creep. So the trade-offs between the deformation mechanisms are governed by work optimization. In other words, the lazy earth seeks to deform in the most efficient way possible. The deformation map also points out another benefit of the work budget, a framework. Unlike Coulomb failure or viscous flow laws, the energy framework applies to all levels of the crust. I'll now highlight two examples of using work optimization to predict fault growth. So in this, once again, looking at physical experiments as our validation, and McBeck devised a numerical model that would query the location and the orientation of incipient faulting. So the question was, can work optimization predict where this new forethrust would form? So this plot on the right shows position of the forethrust on the horizontal axis and orientation on the vertical axis. And we found that this combination of parameters what optimize the external work. That optimal position and location are here overlain on the shear strain map. The shear strain map shows in yellow where the forethrust formed in the experiment, and the optimal forethrust, along with the 90% confidence in these thinner white lines, matches very well the observed forethrust. In another example by Yakubsky et al., they use a different methodology, but the same idea of using work optimization to predict faulting, this time in the Andean foreland, so on a crustal scale. And when they compare the work optimization prediction for the forethrust pattern with the observed changes in contraction across the margin, they find favorable comparison. In this talk, I've demonstrated some of the opportunities gained by framing deformation in terms of the energy budget and work optimization. To constrain the energy budget, you need to know heat, strain, and stress. Heat and strain components of the energy budget can be constrained from some directed observations, but the stress state needs to be inferred from models or through rheologic constraints. So to get the energy budget requires integrating insights from a wide range of field, laboratory, and modeling studies. I've given you a few examples of that in this talk. The energy budget also provides a framework that facilitates interaction between disciplinary silos. We can, for example, formulate how the change in gravitational potential due to reverse slip drives sediment transport. As we consider how energy is transferred from one part of the origin to the other, we start to bridge some of these disciplinary silos. I also want to highlight that within the recent document of the Tectonics community vision, energy budget ties into grand challenges of variations of rheology through the lithosphere, understanding fault zone behavior, and understanding dynamic interactions among Earth surface processes and tectonics. I've shared with you some old and new ideas on the energy budget of orogenic deformation. I'm curious to see what question this framework might inspire for you. Thank you.